Hello, everyone, and welcome to my research presentation on the cryogenic star tracking attitude regulation system, or CSTARS for short, to Imaging Sensor Emulator. My name is Alberto Tabares-Galarza. My research mentors have been Dr. Dorian Petru and Dr. Michael Zemkov. This has been a joint research project between the Astrophysics Department and the Electrical and Microelectronic Engineering departments at RIT. This work has been sponsored by NASA and the RIT McNair program during the summer of 2021. Now, a quick table of contents of what I will be going over in this presentation. First, I wanted to take some time to talk about sounding rockets, the cyber project, how CSTARS connects with the cyber project, the research goals and objective of CSTARS, and the image sensor emulator that I've been working on, the various tasks of my emulator, and the overall development of it. Now, sounding rockets. A sounding rocket is a one or two stage rocket used for experiments in the upper atmosphere. The launch takes roughly 30 minutes and it uses an attitude control system to help keep the rocket or payload on target while it is doing its experiment. And as you can see here, once it gets into its experiment, it needs to use an ACS or attitude control system. Attitude is a change in orientation, rotational orientation. And we want to make sure that while our payload is doing its experiment, that it doesn't get off target at all, so we can collect accurate data. So the CYBER project, CYBER stands for Cosmic Infrared Background Radiation Experimental Rocket. This rocket is a sounding rocket used to collect data on extragalactic infrared background light to search for signatures from first light galaxies. And based off this data, Cyber plans to characterize sources of this radiation to collect information on the beginnings of the universe and the cosmos. So these are two um, figures of the Cyber One project. As you can see, there's lots of telescopes on the Cyber project, and this is what it uses to collect data. And behind all this telemetry is a side-facing star tracking camera that was used for attitude control. So the issue with Cyber 1 was when it was entering the atmosphere, the radiation shield heated up very rapidly. And once it got into its experimental phase, the radiation shielding started to cool down, leading to warping. Now, with the side-facing star tracking camera, it saw this warping in the rocket skin and thought the rocket itself was rotating. And so it told the rocket to compensate for this. So over time, during the experiment, the data was slightly skewed. And this led to not the most accurate data being taken. So this is where Cyber 2 comes in and where C-Stars comes in. So on Cyber 2, to fix this problem, we have the CSTARS attitude regulation system. So we are using warm and cold electronics. That's where the cryogenic part of CSTARS comes from. The cryogenically frozen part is going to be the image sensor. We want to cryogenically freeze it to have it work as best as possible and to also be put within all of the other cryogenically controlled detectors of Cyber 2. So we have a cold payload and a warm section of the payload. And this is where the brains of CSTARS is going to be held. And the warm electronics, or our interface board, is what's sending the control signals and receiving the images from CSTARS and then doing the star tracking and taking those images and calculating the attitude or change in attitude over time. So our research goals are to continue the performance of the CSTARS-2 system and to create a better means to test and debug the system once it is inside the payload. Once we put the electronics within the rocket, it is very hard to take them back out. But we do have access to the cables that they communicate from. So this is where my emulator will come in. I would be able to connect my emulator to the cables that our two electronics communicate to and test them for proper performance and make sure that there is no problems before we send the rocket into space. So my research objective is to emulate the response of the CIS-2521F imaging sensor using a field programmable gate array. This right here is an image of our warm board and the brains of the operation. And here is our imaging sensor on a focal plane board. The tasks of my emulator is it has 4 tasks. First, it will check the power up sequence to make sure that the focal plane board and the image sensor is getting the correct power up sequence from the warm electronics. Then we check the voltages of the power supplies to make sure that they are all within the correct voltage. And then we emulate the response of the imaging sensor running in rolling shutter and global shutter mode. The difference between rolling and global is rolling shutter will expose one row of the imaging sensor to light one at a time and then send that data to the warm board, while global shutter needs a lot more control signals from the warm board to tell it how much to expose the frame of the imaging sensor to take a picture. So global shutter takes one frame of data just at once and then sends all that data, while rolling shutter takes one row at a time, which can lead to artifacts or error in the picture. It doesn't make the most clear picture. So we want to, in the end, have our imaging sensor running in global shutter to help with the attitude control. So the basics of my emulator. The main use of it is to be used for diagnostics and troubleshooting. We want to be able to test the warm and cold electronics once they are within the payload to make sure that they are working correctly. The basics of my emulator runs off hardware description language, which is a special type of coding, and uses special electronics called ADCs and LLSs, which I will go into later. So, hardware description language. Hardware description language is a coding language that hardware synthesis tools can understand and transform into low level circuitry. And this is the board that I'm using, the DE0 Nano board. And it comes with an 8-channel A to D converter, or an ADC, which is very useful for one of the modes of operation of my emulator. So a quick Verilog example of hardware definition language is here. So this is a really simple multiplexer, and I use this to control what operation I'm having my emulator run in. As you can see, this just looks like code, but the beautiful thing about this is this software and the board is able to take this and turn it into a circuit that runs exactly how I tell it to with the behavior that I've coded here. And so this, what it allows me to do is it allows me to use 2 of the 4 dip switches on my board to control what mode of operation I'm in. And this allows me test different to test different modes of not only my emulator, but also the warm board and how it reacts. So ADCs. So it stands for an analog to digital converter. And so we have an 8-channel ADC on our DE0 nanoboard. And what it does is it's able to look at an analog signal like a voltage coming from the warm board, and then convert that into a 12-bit digital signal that the board can understand and relay information back to the user. So using this, I want to be able to check the 8 power supplies that are coming from the warm board and check them that they are at the correct levels that they need to be for correct operation of our cold sensor. So this is a quick implementation of my ADC. What I did is I had 4 potentiometers here, which are just resistors that I can change the values of. And I had them with different voltage potentials across them. The one on the right being the highest and slowly going down as we go to the left. And I wrote a code that could simultaneously look at all 8 of the channels and then send that information back to us. So I use this software called Signal Tap, which allows me to see in real time all of the signals that are coming to and from my FPGA. And using this, I was able to test if my ADC behavioral code was working correctly. And as you can see here. So the first channel here has the highest voltage. You can tell by the most significant bit being on. And as we go down, the most significant the the most significant bit that is on shifts to the right, meaning that the value is going less and less. So this showed me that my ADCs were working correctly, and I translated these 12-bit codes into voltages, checked the voltages, and they were all correct. The last 4 channels just have random values because I left them floating. I didn't connect them to anything, but this showed me that my code worked and I knew how to use the ADCs. So after I got past that hurdle, the next hurdle was learning to use logic level shifters. We found out that the FPGA cannot modulate its voltage on its input and output ports. So I had to use a logic level shifter, which allowed my 3.3 volt logic from my warm board to communicate with the 1.8 volt logic on the interface on the warm board and on the sensor. And this is a little illustration here of the ADCs of the logic level shifters I was using. We're able to give them both a bias voltage, allowing me to put 1.8 on one side, 3.3 on the other, and it allows the electronics to communicate with each other without them damaging one another. Now, this is the final diagram of my emulator here. The mux that I showed you earlier is right here, and what it allows me to do is send a different enable signal to each one of these blocks here. And every block here is a behavioral code that I wrote and spent time debugging and testing to make sure that it was the correct operation. And so using my dip switches, I'm able to turn on and off each one of the different modes of operation and reset them when they don't have an enable signal going to them. And so this is my emulator in use, connected with the warm board. And we were able to send data from my imaging sensor emulator to the warm board and have it understand it and give us an image out. And these are all the references that I have used in all of my images here. Thank you for listening to my research presentation. Have a great day.